Thank you so much, Aaron. So it's good to be here. I'd like to first thank the organizer for inviting me back to Australia. It's great to be back to the other side of the world. Enjoy some sun instead of a gloomy day in Paris. But yeah, so today I'm going to tell you a little bit about Gabriel's theorem and how one can extend it so that it's no longer just ADE, but get ABCDEFG and also HR classical. So let's start off with the classical theory first. So Gabriel in the 70s say that, well, on one hand we have the representation of quivers, and we can study and we can ask about questions on the indecomposable representations. And on the other hand, we also have root system of its underlying graph, maybe it's here, or the ones that are associated to the algebras. And we can ask questions about the positive roots. And if we want to know which kind of quivers have only finitely many indecomposable representations, again up to isomorphisms, then it turns out that it's classified by the Dynkin diagrams, which are the ADE Dynkin diagrams. And moreover, on the other hand, we also have the classification of root system, or if you like, those that have finitely many positive roots, or its underlying wall group is finite, which also has the Dynkin diagram classification. Okay. And moreover, the indecomposable representations, the class of the indecomposable representations are related to the positive roots by just taking the dimension vectors of these representations. And then, moreover, later on, Bernstein, Gelfand, and Ponomarev really realized this connection with Coxeter groups in a more explicit way, which is defining reflection functors, which should be thought of as like a categorify reflections for Coxeter groups. Then later, shortly after, actually it was already written in some ways in Gabriel's paper, Dlab-Ringel showed that, well, if we actually allow ourselves to study valued quivers, then we can now extend this classification to include the BCFG types, so that now you actually get the classifications of all root systems that arise from the algebras. Okay, and all the stories kind of still make sense. Like you can still define reflection functors, which induces equivalence on the derived category of representations, so on and so forth. But what I really want to focus on today is like this part of this picture here. It falls under Coxeter theory, and many of the proofs, in particular, if you're looking at Bernstein, Gelfand, Ponomarev's proofs for the bijection between the indecomposable representations and positive roots, they use a lot of Coxeter theory, or at least results that came from Coxeter theory. And to me, it felt kind of weird that, okay, so we now have ABCDEFG, but where did H and I go, right? I mean, hopefully there should be a picture that actually completes this whole thing. And that is exactly today's goal. So what I'm going to tell you today is that I'm going to introduce you a notion of quiver, a generalized notion of quiver, which I'll call Coxeter quiver, motivated by the classification. And I'll try and introduce to you what it means to study a representation of this kind of quivers, and prove this theorem, prove this Gabriel's theorem, which says that, well, on one hand we have representation of Coxeter quivers, and on the other hand we have root system over fusion rings, which are some kind of root system which might be a little bit weird, but it's studied by Dyer in 2009. I'll explain a little bit of that later on, and we'll have all this similar story going on. The indecomposable representation is going to correspond to finite positive roots. Now our classification of the finite-type quivers is going to correspond to all the Coxeter-Dynkin diagrams, so that we now get the H and I type included as well. And finally, we also have this categorify picture where the reflections of Coxeter groups are going to be categorified into reflection functors, or derived reflection functors, if you like. Okay. All right. Any questions with the big picture for now? Yes.
I have no idea what type HI is. Is that okay?
That's going to show up as an example. So it should be okay. So we'll see it in a very short time.
So can you say again what Q bars?
Sorry?
Can you say again what Q bars and BC?
Yes. So they are going to be valued graphs. So meaning it's the same thing. So with
It's the same as the string on the left hand side.
Oh no, sorry. So on the left hand side, Q is a quiver, and this one is a graph. So I'm forgetting the orientation. Sorry. My bad. Yeah, I should have mentioned that. Yeah. So Q bar to me is just the underlying graph where you forget the orientation. Yes. So I mean, in terms of going back to valued quivers, I guess in some sense, like for valued quivers, you kind of forget the orientation, but one of them gets stuck because you need the B and C difference. But maybe one thing that's worth mentioning now for me is that technically what's going to happen, because I'm thinking about things in terms of Coxeter groups, B and C are going to be the same. Okay, B and C are going to be the same. But okay, so let's start with the definition. So it's not so this is a very easy definition. So a Coxeter quiver for me is just going to be a quiver where you're now allowed to label your errors. Okay, so following the Coxeter theory convention, what you do is that given an errors, now I'm allowed to label my errors as 3, 4, 5, 6, so on and so forth. Some natural number. I'm not allowed, I wouldn't allow myself to label infinity, but you should think of it as like if an infinity should pop up, it should be 2 errors. So it's similar to like the usual quiver case where affine A1 is 2 errors instead of labeled by infinity. So that's similar here. And you should really think of a classical quiver as just a Coxeter quiver where the only numbers that pop up is the number 3. So meaning all of my errors are labeled by 3. And again, following the Coxeter theory convention, I'm going to draw my quivers, my Coxeter quivers as such. Meaning, if it's labeled by 3, I'm just going to drop the label. Okay. So again, this is just convention. If you're not familiar with this is just convention for the time being. And if it's labeled by some other numbers, I'll just write it on top of the errors. Okay. And for this talk, we're just going to assume that our quiver is always finite. So what that means is that my vertices, the set of vertices is finite, the set of errors is also finite. And I also assume that my quiver is acyclic, just to make things a bit easier. Okay. All right, so before I tell you what a representation of a Coxeter quiver should be, let's just look back a little bit on what it. Yes, sorry.
The second example, there's no Coxeter group.
Yes, there's no Coxeter group, so that's fine. So that's something new. That's right. That's right. You should think of this as the similar case where back in the usual classical quiver case, like I'm allowed myself to have 2 vertices and 3 errors. It's not going to correspond to any Coxeter group at all, but that's fine. Good. Yeah. Okay. So before I tell you what a representation of a Coxeter quiver is, so let's just go back and I'll just use the definition of a representation of a value quiver as an example. So back then, a value quiver would look something like this. It's going to be an arrow labeled by a tuple of integers. And what changes compared to quiver representation is the fact that instead of using a representation with the same underlying field, I'm allowing to change the underlying field a little bit. So in particular, I'm playing around with field extensions. So for example, in this particular example there, you should think of it as B2 or C2. A representation of that value quiver right there is going to be a vector space in the real numbers, so over the real numbers, and a vector space over the complex numbers. And in particular, the fact that this V alpha here needs to be in VC means that I'll need to do some sort of field extension. Okay. So what's important for us today is that depending on the label of our arrow, I'm going to do some sort of tensor product to extend it. To extend before I start. So for this kind of representation, this is something that you give, this is something that you give, and this comes attached with it. Okay, so that's fixed. Okay. Yes.
What is the quiver in this case?
Oh, this one right here.
But
it's a value quiver.
What is the parentheses 1, 2 mean? Do you mean there's 2 arrows? And
No. So the parentheses, you should think of this parentheses 1, 2 as a I mean, a value quiver by definition really is just quivers where your arrows are labeled by tuples. But in terms of thinking about it, you should think of this as like it means that you need a field extension of degree 2.
I thought no. I guess so. This is not a Coxeter quiver. Oh, this is a.
Oh, this is value quiver. Sorry, this is the motivation of what I'm going to tell you next.
Okay.
Sorry. Maybe I wasn't clear. Yeah. So sorry. This is the motivation of what I'm going to tell you next.
And V alpha is a map of complex vector spaces then?
Yes. So V alpha is a map of complex vector spaces. So Vj is a complex vector space. Vi is a real vector space.
Yeah.
And because this comes attached, now this one right here really is a map of complex vector spaces.
And the 2 is what told you need to complexify?
Yes, in some sense, yeah. So technically you need both 1 and 2. I'm hiding some details right here, but for this one, you can just trust me that this is one example. All right. So for us today, so for me, a Coxeter quiver representation will look something a little bit similar. So if I give you a Coxeter quiver, which looks something like this, maybe in this case, just two vertices I and j, and with a single arrow labeled by V alpha. a representation is just going to be giving me some sort of vi, which is living in some category, vj living in some category. V alpha is also going to live in some category, but the important fact here is that we're going to tensor by some object depending on the label of our errors. Okay, and these kind of categories that I'm going to build on are called fusion categories. And here's what it means to be a fusion category. It really is just a C-linear fusion category. A fusion category is a C-linear, a Boolean category, which is semi-simple. We find out many simple objects. It's also a monoidal category, so that we have tensor products attached to it. And it's also a rigid category, so that we have left and right tools. So for those of you who are not really too familiar with this notion, you should really just think about this for the purpose of this talk, that they are just vector spaces with non-integral dimension. Okay. And in particular, very important numbers that are going to pop up for us today is that we really want objects which has dimension or quantum dimension of 2 cos pi on n. Okay, because these are numbers that really shows up a lot in Coxeter theory. So these are the type of fusion category that we're interested in is really it's just the fusion category that's associated to the UQSL2 representations. Or if you like, for me personally, you can also use the temporally Jones category, which is like objects are just the Jones-Bendel projectors, so on and so forth. Okay. So again, don't worry too much if you don't know what this is, because I'll show you a very specific example in a very short time. And so for each n, I'm going to consider such a category. So Cn is going to be the fusion category associated to UQSL2, where my Q is evaluated at the 2nth root of unity. So something dies off and then you semi-simplify it. That's the main idea. And for given each quiver, I'm going to define a fusion category which is just a tensor product of all the labels that actually shows up. Okay. So CQ is just going to be the so this one right here is the least tensor product, but really the naive tensor product would have worked. Okay. And in particular, what's important for us is that when the image when the only labels that shows up is the label 3, then CQ is really going to be equivalent as a fusion category to the category of vector spaces. Okay. So again, for the experts right there, technically I kind of like when n is odd, I'm only going to take the even part, which is why the last remark here proposed. So I'm only going to take the even parts of the category. Okay, so here's what it means to be a representation of a Coxeter quiver. So as we've seen just now, to each vertex, I'm just going to attach an object in CQ, which is the category that I built just now. And to each arrow that I have labeled by V alpha, you'll need to give me a morphism W alpha, which is in CQ. But now this is going to be an object that depends on the label right there. And in particular, this object is exactly the object that is going to have the quantum dimension to cos pi. Okay. And the morphism is defined the same way, where it's just a set of morphisms where on each vertex you give me an actual morphism between the Wi and Wi prime, and you want to make sure that the diagram commutes. So this is going to be similar to the quiver case. And I guess the only extra condition, if you haven't seen the value quiver representations before, is that you want to make sure that this step here is the identity. So remember that you're not allowed to touch this part of the diagram because that's fixed. That's given to you. That's not something that you're given. Yep.
So you fix these objects A sub V alpha
Yes.
line?
Yes.
For each V alpha, there's one object.
Yes. For each V alpha, there's going to be one object. That's right. Yeah. So again, for the experts out there, the V alpha is going to be the generator of the category. So UKSL2 is the fusion category of UKSL2 is generated by one object, and that's exactly the object that we're looking for. Cool. So let's now see. Sorry. Yep. Sorry.
In the case of UPSS, the alpha can only be 2. Or
The
you
alpha.
only have one.
Oh no. So no, that's not right. So in the case of UKSL2, what changes is the value of Q. So because Q is evaluated at the roots of unity, nth roots of unity. So you're depending on the roots of unity, you take different objects. And finally, just to quickly mention that rep Q is again abelian. In the same way that Y representations of quivers are abelian, you just take kernel and co-kernels and component wise in the same way. Okay. All right. So now let's see an example. All right. So to answer your question, the H2 graph, or sorry, the H2 quiver or the I2 5 quiver is going to look something like this. It's just two vertices and one arrow with a label 5. Okay, so very simple quiver. But in this case, so our fusion category that we're going to look at is the golden ratio category. It's a very simple category. It only has
Fibonacci.
yes, or Fibonacci category. Yes, I should mention that. So pick a poison, whichever one works for you. So, but what's important for us today is that this golden ratio category is basically just a slight generalization of the category of vector spaces. So back then, the category of vector spaces, you have exactly one simple object up to isomorphism, but now we have two non-isomorphic simple objects. And there's an interesting tensor product going on, which looks something like this. Which pi2 tensor pi2 is going to be isomorphic to pi0 tensor by direct sum with pi2, and it really is like the categorify version of the golden ratio relation. Okay, and in particular, the golden ratio is exactly 2 cos pi on 5. So pi0 is going to be our monoidal unit. So it's and pi2 is exactly the one with the quantum dimension golden ratio, or 2 cos pi on 5. Okay, and so. And a representation of this quiver right here, the H2 quiver, is just going to be something like this. On each vertex, I can attach some object or even a 0 object if you like. And again, whatever that's labeled in green, you're not giving that data. Like it's a fixed data that's given that's by definition going to be there. Okay, so in this case, you're basically just giving pi0, 0, and 0, 0, pi0, and 0 itself. And similarly here, you're just going to give me pi0, pi2, and the map, which is an isomorphism in this case. Okay. And what's interesting about representations of quivers in this kind of case is that now you kind of have a right action of your fusion category as well. Because what you can do is that you can start off with the representation that you're given and tensor on the right hand side. Right? You can tensor on the right hand side, and then that gives you a new representation again. So starting off from 5 of these representations on the left-hand side, after tensoring by pi2, we get 5 more new, right? I claim to be new representations on the right-hand side. Okay, and my claim is that these are going to be the 10 indecomposables, but we'll come back to that later on. So in particular, given this kind of structure, what RepQ has is what we call a module category or a right module category over the fusion category CQ. Okay. All right, any questions about this particular example? Yes.
I guess just in principle, so a free-labeled edge and a simple edge would correspond to tensoring the pi0.
Yes, that's right. So if I want to extend this example a little bit, so let's say we add another vertex here and just an arrow right there, then you just have something right here which tensor by pi0, which is just the same thing. That's right. Yes.
It's always pi n minus 3.
Yes, it's always pi n minus 3. That's right. You could play with pi1 if you like. So the other,
Yeah,
but then you have doubling things out, so on and so forth. So yeah.
So how do you choose that?
Sorry.
Why is it pi n minus 3?
Pi n minus 3 is the object with quantum dimension 2 cos pi on n. So in this case, in this category here, pi n minus 3, which is pi2, is the only object with quantum dimension 2 cos pi on 5, which is the golden ratio. So you're always going to pick the object which has quantum dimension 2 cos pi on n, for n being the label of the error.
I mean, so I was going to say there's 2 such objects and then.
Yes, there's 2 such objects when n is even, but I'll just pick n minus 3 to make this easier. That's right. Instead of pi1?
Instead of a random other.
Okay. So it's not clear now, but 2 cos pi on n is a very important number that's going to show up in the representations of Coxeter groups. Okay, we'll see more of that when it comes to the root system. Okay. Yes, okay.
No, it's covered.
Oh, it's covered. Okay, yeah. So for the time being, take it as it is. For the time being, this is really just a totally new thing that I'm introducing to you, which seems totally weird, but everything will slowly make sense. Hopefully. Yes.
So you have many choices. You have the choice of the pi2, and you have the choice of the next, all different choices.
Yes, all these choices. So there's 2 types of choices that maybe I should be clear about. So one of them is really fixing pi2 is by definition. The choices of the map is what you're telling me to be a representation. So that's part of your data, it's not my data anymore. So the game is that I'm telling you the definition is that you need to tensor by pi2, but you will need to tell me the map.
And everything also depends on in this case, not on your orientation, but general orientation.
Yes, it depends on orientation. Yeah, so this one has not many interesting orientation, that's right, but it does depend on the orientation. Yes. Good. Any other questions?
Yeah, I also don't understand. Yeah.
Okay, all right. So now let's go back to unfolding and I'll try and prove Gabriel's theorem in a very short time. Which is back then, like I think studying quivers, like it's very common to study non-synchronized quivers by studying foldings. So for example, if I start off with the did I write D5? Sorry, I meant to be it's meant to be D4. So if I start with a D4 graph or a quiver, you can fold it by studying a Z mod 2Z automorphism, which swap these two, fix this one and fix this one right here, and that folds you into the type B3. And similarly, you can also start with the D4 graph and you study the Z mod 3Z action, which cyclically permute all of the outer vertices and fix the one in the middle, and that folds onto the G2 graph. But there are also certain types of folding which was studied by Lustig that are not they're not really coming out from automorphism. They're kind of the weird ones, if you like, which is something that looks like this, where if you start with the E8 graph, you can fold it into the H4 graph. Again, here's another example of the type H graph. You can fold into the H4 graph right here by basically just mapping them down this way. Okay, it's no longer really an automorphism, but again, it's kind of controlled by the golden ratio in a certain sense. But what's important for us today is the fact that whatever this kind of folding is, what Lustig called the admissible folding, is always going to induce a injection between the Coxeter groups. Okay, so whatever kind of folding that we have right here, reverse specific example that I'm showing you right here is going to inject it's going to give you an injection between the Coxeter groups, and all that you do is that in terms of Coxeter groups, you're just sending the generator here to the product of these two generators, which always commute. So that's one of the definition that why it needs to be how it needs to be an admissible folding. It needs to be disjoint. Okay. So for us today, so we started off with the Coxeter quiver, then we're going to do something which is a little bit different. So in Lustig's study, you start off with a quiver and then you fold it into a non-synchronized quiver. So we're going to start from a Coxeter quiver and unfold to get a usual quiver again. So given a Coxeter quiver, so you can define a classical quiver, which I call Q check, where the vertices are just going to be the product of the vertices of my Coxeter quiver and all the possible irreducibles that shows up in, or the simple objects that shows up in my fusion category. And I have an arrow between them if I had an arrow between in the Coxeter quiver right here between the original vertices, and the object B shows up as a direct summand when I take A and tensor by the special object that I picked. Okay, so you get arrows like this. So just to show you a specific example, let's say we start with this quiver right here. So we have 1, 2, 3, 4 as our vertices, and then so again in this case the fusion category CQ is exactly the same category that I showed you just now, which is the golden ratio category or the Fibonacci category. And the way that you unfold it is again like for each vertex you're gonna have two vertices on the unfolded side now, because you have two simples. We have two non-isomorphic simples, and they are related whenever it appears at the summand. So for example, let's see. So pi 0 tensor by pi 2. Again, remember pi 2 was given. Pi 2 is exactly A B alpha in this case for that one. So pi 0 tensor by pi 2 is going to give you a summand of pi 2. So therefore, you have an arrow going to pi 2. And similarly, pi 2 tensor by pi 2 has both pi 0 and pi 2 as a summand because of the golden ratio relation. And therefore, we have arrows in both cases. Okay. So and this model is exactly Lustig's folding of the E8 into the H4.
Why do you have the map from pi 0 into the pi 2, the lower one?
Yeah, because pi 0 tensor by pi 2.
Oh, it's always just tensor by
Yeah. So on this part right here, it's always tensor by pi 2.
Okay.
So pi 2 tensor by pi 2 is pi 0 direct from pi 2. So you have two arrows. Yes, yeah. Because this one up here are all labeled by 3, which is tensoring by pi 0.
Yeah.
That was yes.
But if I tensor pi 2, because I started 2 pi 2.
Yes.
I tensor with pi 2.
Oh no.
Yeah.
The data yes the data is tensoring by pi 0.
Yeah.
Wait, good. Is that clear now? Yes.
I just wanted to remind it one more time. So the overall fusion category that we work in is tensor product for all the edges, or
Yeah.
what?
The tensor product for
Tensor product for all numbers are varying on the edges.
Yes, that's correct.
Which is
Oh yeah, I guess yes. The numbers depend on edges. Yeah.
For
So
some reason I thought it was a direct.
no, it's a tensor product. Sorry, yeah, it's a tensor product. So I mean, for all the finite type examples that you're gonna see, somehow you only need an actual fusion category of UTSL2.
I understand.
Yeah, but if you work with weird ones, then you're gonna get fusion categories which have different labels and tensor with different stuff.
That's it.
Yes.
So the tensor product is just like tensor and
Exactly. So the tensor product is basically just a product category. Your simple objects, it's very close to product category. I mean, your simple objects are exactly the simple on each of them, and the Hom spaces you take the actual tensor product of the underlying vector spaces. So in particular now, if you, for example, you have simple objects and zero object, that object is going to be isomorphic to zero, for example. Cool. All right. Any other questions with this unfolding? Okay. All right, so let's go back to the example that we were working on just now. So if we start off with the H2 quiver right here, then it's going to be a bit simple. All that we're unfolding is basically just the one part of this diagram right here, right? We're just taking this part right here. So all we're getting is like the A4 graph. Sorry, the A4 quiver in this case. Oriented. So sorry, one thing that I didn't mention is that the orientation does depend on what the orientation of this guy is. So for example, because it's going this way, then this is not a linearly oriented quiver. It does depend on the orientation. So if we study the representation of this Q check here, which is the A4 quiver, then we know that it's just given by closed intervals of integers of ones in this case. So there's exactly 10 of them. Okay, there's exactly 10 of the indecomposables. And similarly, as we were seeing just now, we have like the 10 indecomposable in this case, right? So we have all these things, and then we can tensor by pi2 and get the other 5. And the claim is that it's going to be exactly equivalent. So what it means is that I kind of started off with something totally weird, and then now we're going back to saying that, well, actually, as a billion categories, they're exactly the same. So, and it's actually not too hard to see how these bijection kind of work, because how the function should be defined. I'm not going to tell you how the function needs to be defined, but I'm just going to quickly tell you at least on vertically how to see it. Basically, in this case, I have pi 0 and 0 here. So on the pi 0 part, I'll just put the one-dimensional vector space, and then everything else is 0. Right? So similarly, maybe let me take a more interesting example. For example, this one right here. We have pi 0 direct sum with pi 2 on the first vertex, so we just have one-dimensional on this vertex and another one-dimensional on the top vertex there. And similarly, pi 2 there, we just get one-dimensional. So in terms of the Hom spaces, there's a little bit of work to do, but I mean, like most of these Hom spaces are going to be one-dimensional. Like remember that our category is like a semi-simple category, so there really isn't not too much to do. Is this one right here? So going from this part to this part is very, very close to almost saying that I'm just going to forget the fact that I am working with a fusion category. I forget about the tensor structure. I'll just want to map it into the category of vector spaces. So it's very close to that. Okay. All right. Cool. So the claim, so the first theorem, which I'm not going to prove, is that these two categories, the representation of my Coxeter quiver and its unfolded representation category of my unfolded quiver, is equivalent as abelian categories. So one thing that I really want to mention here is that what's new that we get is that actually RepQ, as we've seen, is naturally a right module category, right? It has the right action of my underlying fusion category by just tensoring on the right hand side. But it's not that obvious at all, like why RepQ had that. If I just given you a random A4 quiver that was oriented that way, why it should really have like a fusion category action on the right hand side. Okay. And just as a small remark that I'm not going to talk too much about today is that for representations of just like representations of quivers back then, you can also define algebra objects within your fusion categories, which becomes its path algebra. It's going to be defined by some sort of tensor algebra within the category. And then in this case, RepQ and the path and the the category of modules over the path algebra is going to be equivalent as abelian module categories. Okay, I know that there's a lot more different module words coming out, but this one is the module category. This one right here is the category of modules over the algebra. Okay.
Module objects over the algebra object.
Yes, module objects over the algebra objects. That's right. Yes. Okay. All right. So now we're gonna prove Gabriel's theorem, because as you can see now, okay, proving Gabriel's theorem, at least one part of it is no longer that hard anymore because we have this connection back to our classical quiver, right? So in this case, just to mention, so Gabriel's theorem for us is going to be Q is finite type, meaning again it's just you have finitely many indecomposable objects up to isomorphism. It's going to be true if and only if it's underlying graph. Again, Q bar means you're forgetting the orientation, but in this case you are keeping the labels. Okay, you are keeping the labels. And so Q, if and only if Q bar is one of these Coxeter-Dynkin diagrams. Okay. So going this way, so from right to left, is basically you can really just go through this list and show that the unfolding you unfold into ADE types. But I think this is a bad proof. We'll see a better proof in a very short time. Just as how Bernstein, Gelfand, Ponomarev gave a better proof of Gabriel's proof as well. But the other direction is probably the more interesting one. So the first thing that you need to do some combinatorial, very simple check is that you can show that as long as my Coxeter quiver contains anything with two vertex of any kind of labels, then it's always going to be not finite type. So that's one thing. That's one small lemma that you need to check. But once we have this, then it's not too bad anymore because all we need to show is that okay. So if we assuming that Q is of finite type, then by the theorem up there, we know that Q hat is also Q check is also finite type, right? And therefore, this means that by Gabriel's theorem, Q check bar, so forgetting the orientation, so on the unfolded quiver, forgetting the orientation is an ADE graph, okay, or potentially disjoint union of them. Okay. And what this means is that the Coxeter group is going to be finite, right? So the Coxeter group is going to be finite by Coxeter classification. So, but using those 6 results, so all these kind of the unfolding that I've given you has a very natural folding map, meaning you just map it back to the first to the vertices, and that is always going to be an admissible folding. It's very easy to check. So by listing result, we know that there's an injection between the Coxeter groups. Okay, so the reason why we needed this is to make sure that because our Q could have not been a Coxeter graph, like Hoyle pointed out. So once we have this, we know that we can reduce to the case where every time when we're given Q, a Coxeter quiver, its underlying graph is a Coxeter graph. Okay, so now by listing result, we know that there's an injection, but since we know that this is finite, this must also be finite, and therefore by Coxeter classification, we're done. It must be a Coxeter-Dynkin diagram, and that's the proof, right? Cool. Any questions up to now? Yes.
So Gabriel theorem also gives some justification of computation in terms of roots.
Yes.
Does that have uniqueness?
Yes, it comes. That's exactly what's going to come next. That's exactly going to cover this part of the better proof of this part as well.
Okay.
Yeah, that's exactly what's going to come next. Yes. Any other questions? Yes. Is it coming next? Yes, it's coming next. Yes, this slide. Sorry, maybe I should have just put this at the very start. I'm sorry. I should have maybe started with the root system instead of the representations. But it's coming now. So hopefully I'll answer your question with it. So if it doesn't, let me know. So this one should hopefully answer it. Okay. So now I'm going to try and talk a little bit about the connection to root system. So usually root system, so for me, so one thing I really want to mention is that usually when one talks about root system, it's always integral root system, meaning within your bilinear forms or the matrix that induces your bilinear form, you're only going to see integers popping up. But what I'm going to show you today is that for these kind of Coxeter groups, it's actually a little bit more natural to think about a symmetric bilinear form, which is no longer integral. Okay, so take this Coxeter group as an example. So for the Coxeter quiver that we saw just now, if you forget its orientation, it really is just the I25 or the H2 Coxeter graph. And in this case, the Coxeter groups are just a dihedral group with 10 elements, or even better, it's just the isometry of the pentagon. Okay, so if we want to really study its linear representation in a very particular way, then this is one way, right? I'll give you pentagon sigma 1. So whichever one that you like, it doesn't really matter. So sigma 1 is going to reflect along this diagonal here, and sigma 2 is just going to reflect along this diagonal here, and it generates the whole isometry of the pentagon, of the regular pentagon, to be more precise. Okay, and so if you write down what data you need to write things down as reflection, then really this is what you have. So on the real space, the bilinear form that you have is exactly for EI and EJ. So EI being one of them, EJ being the other one of them. So for EI and EJ, if they're the same, it's like 2. It's up to you. You can even pick one and just chuck the 2 at the front if you like. But if they're not the same, it's going to give you negative 2 cos pi alpha, exactly because of this angle right here. Okay, so it's going to give you negative 2 cos pi alpha. Okay, so that's why you need 2 cos pi over 5, because the linear, in some sense, the linear reflection tells you that you need these kind of numbers. Okay, right, and in particular, once you're given this bilinear form, you define reflection in exactly the same way, just b minus the usual sum. Okay, all right. So instead, so exactly because of that, like because of this number here is no longer an integer, what the kind of lattice that you get is not really an integer lattice anymore, right? Like you get like this weird like golden ratio numbers popping up here and there. So it's more natural to really, so instead of starting R, so back then you would start from R and restrict yourself to C to study the root system. Now you're gonna start with R, restrict yourself to Z adjoint delta, right? I mean that's the most natural one. Okay. So this is going to be a ring, and this is going. This is not really a lattice, but at least it's still like, I mean it's still a free module over this ring. Okay, and and in the same way, so the way that you define what are positive roots is you kind of do the same thing. So these two, you start off with 2 simple roots, and then the roots are just going to be the orbit of your group acting on these elements, and the positive ones are the ones where it is exactly lying on one part of the plane, or if you like, only delta pops up. Okay, no negatives pops up. In this case, it's very explicit. Okay, so you have here you have 5 roots, and the other negative roots are all the negatives of all of them. Okay, and a lot of properties that you know from root systems of Coxeter groups can also be shown for these kind of Coxeter system, meaning they're always going to be either positive or negative, so on and so forth. There's always, for Coxeter groups, there's always this kind of classification. Okay, and what's going to be a little bit new is that now we can also study extended positive roots. So we start off with 5 positive roots, and then the extended positive roots are exactly the ones that are just multiplied by one single scalar. Okay. On this picture, it's not really that obvious what one should really, or how one should really define extended positive roots. But if we realize that the golden ratio category, like the one that we have just now, if we study skew ring, or if you like, it's basically the Grothendieck group where I now impose a ring structure on it by saying tensor product gives you multiplication, then this is really just Z delta. This is really just a fusion ring. And what I mean by an extended positive root is just saying that it's given by a multiplication by the class of an object, which is indecomposable. Oh, sorry, which is a simple object in this case. So it's just an extended positive root is just any positive root that you have just now multiplied by a class of a simple object. So in this case, we have 2 simple objects, therefore we have multiplied by 0, which gives me this one here, and then sorry, multiplied by pi 0, which is multiplied by 1, gives me this one here, and then extended 1, which is this one right here. So we start off with 5 positive roots, and then the extended 5, we have another 5 extended positive roots that goes up. Okay, yes.
Extended root is like,
yes.
Where does it come from? Like,
So the positive roots are exactly the orbit of the simple roots. So you get 5.
Yeah.
Sorry, the positive roots. So you get 5 positive roots. An extended positive root is just any element in this lattice, which is just given by a positive root multiplied by the class of a simple object.
why do we want to do that?
Okay, I mean so if you really want to make things a bit more precise, I guess you'll need to go with Dyer's work, which is not categorify. I'm just telling you the bigger picture, which is coming from the categorify version, which is much easier. Which is okay. These things are just the positive roots, but Dyer has a different definition, because in his case he were really just studying root system over any kind of commutative ring. Okay, commutative ring based and with a positive structure is what he calls it. But again, like in the categorify picture, that is exactly what it is. I'm just giving you a simpler picture, so you kind of need to take it as it is. And there's also a good reason. Okay, maybe this might convince you a little more. If you take, so remember that we say that the H2 Coxeter group embeds into the A4 Coxeter group, right? Because that's what the Lustig folding is. So that was a 4-dimensional space, right? If you pick your plane correctly, if you pick a 2-dimensional plane correctly, you cut through the 4-dimensional space. The 10 positive roots that you have in your Coxeter group is exactly going to be this one here and this one right here. So maybe that's a better answer for the timing.
This is a general thing.
Exactly. So if you cut through the plane, you're always going to get all the other roots as the extended positive roots. Okay. So in this case, it's a 4-dimensional space cut off with a 2-dimensional plane, and then the 10 positive roots are all run as a positive roots and extended positive roots.
So how do you see the possibility with 10 registrations we had before? So there should be half of this that not taking this.
Yes. Yes, we'll see that right after. Good. Okay. All right. Any other questions? No. Okay. All right. So here's Dyer's again Dyer's definition, but me putting in the categorical framework to make things a little bit easier, at least for me. So for us, like given the Coxeter quiver, the lattice that we're defining is really just the the fusion ring of my category CQ. Direct sum however many times depending on the vertices. So then now we get some sort of lattice. And the bilinear form that we define is exactly the ones that we had just now very similarly. So sorry, this should be A B alpha. So which is why the n minus 3 comes up. But so this is just A B alpha, the minus of the class of A B alpha, and the rest is just the usual sum. So this is 2 times 1. Okay. And again, the way you define reflection is exactly as what we've seen just now. And this the Coxeter group or the related reflection group of what you're going to get is exactly just generated by these sigma i's. Okay. Okay. So and as we said just now, so the simple roots are exactly the EIs that we have just now. The set of roots is just the orbits of my roots, and the extender are exactly the ones where for each of my roots I will just take the simple object and multiply the class on it on the right hand side. And finally, a positive element is just saying, in this case, this, again, on the categorical level, it's very easy to see what it is. It really is just, positive just means that it really is coming from an object. All right. Okay, and now, so dimension vectors is no longer that hard to define anymore once you've convinced yourself that, these whatever rings that we're working just now were all just fusion rings coming from categories. So given a representation, then the dimension vector is really just saying that on each of my vertex, I'm just going to take the class of that object and write it out as a dimension vector. I mean, to be frank, this is exactly going to be the same. If you really want to, you can also say that the dimension vector is really just taking the growth of the class, because that's going to be isomorphic as 3 modules anyway. Okay, right. So okay, so to study this kind of to relate the indecomposable objects that we've seen just now to the extended roots. So here's maybe let me just state the theorem first. So if we're given a Coxeter-Dynkin diagram, then the dimension map, meaning this one right here, defines the bijection between the indecomposable representations and the extended positive roots. Okay, so it is the extended positive roots, not just positive roots. But moreover, the lifted definition of extended positive root works as well. Meaning, for every indecomposable object, which is now an extended positive root, you can moreover write it out. It's going to be isomorphic as an indecomposable representation tensored by actually a simple object. So it's not just true on the grothendieck level, but also true on the categorical level as well. Okay. And the proof that we're going to use is exactly what BGP did. So Bernstein, Jeff and Ponomarev, we're just going to define reflection functors. And remember that reflection functors are actually just defined in terms of kernels and co-kernels. I mean, there's nothing really specific about category of vector spaces. And all the categories that we've been working up to now are abelian categories. So taking kernels and co-kernels works perfectly fine. But we'll see it again. We'll see in a very specific example later on. But what's going to be important for us is that the fusion category, the monoidal structure is actually exact, is bi-exact, right? So now whatever reflection functor that you're defining in terms of the abelian category that you're using for the fusion category that you work on, it will always preserve the left action, because tensoring is an exact structure in these cases. So the reflection functor, so I guess this one right here is going to be exactly the same as what you would get back then. The dimension commutes with the reflection functors, as long as you're not a simple object. But this one right here is, I guess, it's a little bit new, because back then this structure didn't really obvious. Okay, so again, it's better for us to see an example instead of looking at the actual proof. Okay, so if we're looking at representations of H2 quiver, which we have up there, we've seen that we have 5 positive roots. And what you can check is exactly that if we now take the dimension of the left-hand side right here. So again, dimension in terms of what I define, meaning you're taking the class of these objects right here. Then these 5 right here exactly corresponds to the 5 positive roots. Okay. And moreover, if I now scalar extend by delta, categorically it means that you're tensoring by pi2, or tensoring by the golden ratio object, then you get the other 5. which is the other extended positive group going out right here. Okay, and again, because tensoring commutes with the dimension, so all these works correct. Yeah. Second. Okay. All right, and in terms of reflection functors, it's not too bad. So let me just show you a very specific example. So let's just take this one right here, and just to make sure that we won't do things wrong later on. So if I take this guy right here, which corresponds to delta delta, which is this one right here, and which is this octave right here, and if I reflect along sigma 2, I should be getting something of delta 1. Okay, so if I now take this representation right here and apply, and I want to apply the reflection functor on the second vertex. So you kind of play the same trick, right? You start off with this representation with this morphism right here. You take the kernel, right? You take the kernel, and then now you have something that's mapping from pi 0 into pi 2 tensor with pi 2. Again, this thing here is the fixed one that's coming from here. But now you want to reflect the arrow, right? Because you apply the reflection functor, you want to reflect the arrow. So the map that we want is actually going from here to here. Right? So we actually want to map from here to here, but remember that our category is also rigid. So that's where the duality really comes in. Because this pi 2 is self-dual, there's always a unique map going the other way around. In terms of diagrammatics, you really just twist everything around. Okay. And so that's exactly what you define it as. So meaning if I take the reflection functor R2 reflected at my sync vertex, then what you get is this one right here. Okay, and that corresponds exactly what we want, right? Because we have now pi 2 tensor with pi 2 tensor with pi 0, right? So we have pi 0 and pi 2 with the map either hat. And so this corresponds exactly it's delta. Right? So we take that into account. So everything checks out. Okay. And so you can do the same thing where now if you apply a reflection functor on the first sync now, following this one right here, you'll get 0 pi 0, which in this case, in terms of the Coxeter group action on the lattice, you just get a rotation of this guy anti-clockwise. So now you get here, and then switch out. Okay. All right. Okay. So yeah. So I guess that's what I want to say for most of today. But I'll just maybe mention a few further directions that one can probably think coming out from this. But maybe one that I'll focus on today a little bit more, since we're in the categorification conference, is the cluster combinatorics. So while I was writing this paper last year, I actually stumbled upon the paper by Gabriel and Markin, where they were doing something quite similar, but from a very different point of view. So they were studying cluster algebras, and it's known that the representations of quivers models cluster algebras, at least the combinatorics, meaning the mutation corresponds to the cluster tilting objects in the category. And so what they were interested in was to actually categorify the cluster combinatorics for different types of quivers. Meaning, once again, like back then, cluster combinatorics were only defined for at least mutations of quiver were only defined for integers. But you can actually study mutations of quivers just as nicely if you just throw in real weights, right? You just throw in real weights. So for example, for those of you who have seen mutation before, but not real weights mutation. So you start with a quiver like this and you mutate right here. What you get is 2 cos pi on 5. So you have 2 cos pi on 5 arrows multiplied by 1 arrow. You get 2 cos pi on 5 arrows on this side. And then you just flip, and then you just flip everything, and then you remove. Instead of removing 2 cycles, you take minuses, right? You just remove ones if you need to. Right? You just don't want anything that goes one way and the other. You just take minuses instead. Okay. And there's also surprisingly a classification for quivers with real weights that only has finitely many mutation classes. The numbers that are only allowed to show up are 2 cos pi on n. Again, I don't know why, but there are a few weird ones which, for example, something like this is also a finite mutation class. So in this case, you have 2 cos pi on 5 and 2 cos 2 pi on 5. And I guess the question really is that, okay, so how do you actually model this? Okay, so what I want to also mention is that Gabriel and Markin really did things case by case. They said that, okay, we'll start with the finite types. I'll show you a folding structure. What they call a folding structure is exactly the fact that our representation of quiver, the usual quiver, the Q check, the folded one, has a module category action. I mean, they didn't really phrase it that way. They were defining semi-rings action, so on and so forth. But really, again, in the categorify world for us, what that really means is just what they call a folding structure is just rep Q check equipped with a module category structure, which is given by the abelian equivalence that we have right there, right? Because rep Q obviously has a module category structure. Therefore, rep Q check has a module category structure by just transferring over the equivalence. So it wasn't really clear to them how they should deal with the other types, because whatever that they were defining right there were a case by case. Okay, we do it for type H and then we do it for type I. I mean, those were the only two that were missing. So they did those two cases and that was it. But now I'm giving you something that's completely general. So take any quivers that you like, take any real quivers that you like. There's always a way to define module category structure. And the question now really is that, okay, for me, at least for me personally, it's not too clear for me how should one model something like this, because this number kind of shows up. I mean, again, it's just convention that because I'm doing Coxeter theory, I prefer to label this like 5 user 2 cos pi 5, but I really don't know what this one should be. So maybe that's food for thought. So thank you.